Okay, so are you ready to dive in? Because today we are looking at plasma physics.
Sounds good.
We're going to unpack some really cool and surprisingly relevant findings from a recent research paper about this really tricky thing called the Landau Equation. And I promise we're going to make this painless, even if you've never encountered plasmas outside of maybe like a high school science class.
Exactly. And you might be surprised to learn just how much this equation impacts some pretty exciting fields, like fusion energy research, and even our understanding of what goes on inside of stars.
See, this is what I love about these deep dives. You never know where we're going to end up. So let's maybe start with the basics. What exactly is the Landau equation, and why should we care about it?
Well, the Landau equation is essentially a mathematical model that describes how charged particles in a plasma interact with each other over time. So think about it like trying to predict the movement of like 1,000 billiard balls colliding on a pool table. But instead of simple collisions, these particles are constantly pushing and pulling on each other with electric forces.
Yeah. Okay, I'm already starting to get a headache just picturing that. No wonder it's a tough equation to work with.
Yeah, it definitely keeps mathematicians and physicists on their toes. One of the biggest challenges is figuring out how to incorporate something called the Coulomb Potential, which is the fundamental law that governs how charged particles attract or repel each other. And it's particularly tricky to kind of integrate smoothly into the Landau equation.
Okay, I'm sensing a but coming here, like this research paper found a way to tackle that challenge.
You're reading my mind. This paper makes some significant headway by looking at a specific type of interaction. That's governed by what are called very soft potentials. These potentials describe situations where the electrical forces between particles are relatively weak and spread out over larger distances.
Okay, hold on a second. Before we get too far, can we unpack this very soft potential idea a bit more? It sounds like it's key to understanding what makes this research so interesting.
Absolutely. Imagine you have a bunch of charged particles bouncing around. With very soft potentials instead of strong, close-range jolts, these particles gently nudge each other, even when they are relatively far apart.
So kind of like the difference between, say, magnets that snap together versus those that have a weaker pull over a greater distance.
That's a great analogy.
Right.
And dealing with these very soft potentials, including the particularly tricky Coulomb potential, is a big deal, especially if you're interested in things like fusion energy, which relies on understanding how plasmas behave at extremely high temperatures.
Okay, I'm starting to see why this is a big deal, but where does this whole Fisher information thing come in? Our prep materials mention that this research had something to do with understanding how information behaves within these plasmas.
That's right. Fisher information in this context is essentially a way to measure how much useful information is encoded in the way those particles are distributed within a plasma. It's like looking at a snapshot of those billiard balls on the pool table. The way they are scattered tells you something about the overall dynamics of the system.
So more information means the particles are in a more complex, harder to predict arrangement.
Exactly. And what makes Fisher information so important here is that it gives us a handle on how smooth or predictable the solutions to the Landau equation are for these very soft potentials.
Okay, so smooth solutions are good because they mean our models are behaving nicely and giving us reliable predictions.
Precisely. Smooth solutions are like having a clear map with accurate distances. They make our lives as physicists a whole lot easier.
All right, so we've got this equation, the Landau equation, that helps us understand plasmas. And we have this concept of Fisher information, which tells us how much useful information is tucked away in the way these plasma particles are distributed. But why is this paper we're deep diving into so groundbreaking? What did it actually discover?
Well, what's fascinating is this paper proves that under the conditions of these very soft potentials, the Fisher information actually decreases over time.
Wait, so the information about those plasma particles is actually fading away. That sounds counterintuitive.
It does, doesn't it? You'd think that with all those particles interacting, things would get more complex, more chaotic, and the Fisher information would increase. But no, it actually decreases, meaning things are becoming more predictable over time. This was a bit of a head-scratcher for physicists for a while.
Yeah.
But this paper beautifully clarifies this behavior.
That's amazing. So are you saying we can actually make reliable, long-term predictions about these plasmas, even though they're incredibly complex systems?
That's exactly what this points to. It's like having a weather forecast that gets more accurate the further out you look, which, as we know, is not usually the case.
That's a fantastic way to put it. Okay, so how did the researchers figure this out? What was their secret sauce?
Well, they used some very elegant mathematics, connecting the Landau equation to a powerful tool from probability theory called the Bakry-Emery criterion. Now, without diving too deep into the theoretical weeds, this criterion essentially helps us understand how systems evolve in terms of their information content. And what they found is that for those very soft potentials, the Bakry-Emery criterion holds true, which directly implies that the Fisher information must decrease over time.
So they found a hidden link between this probability theory tool and the way these plasma particles behave, which unlocked this whole new understanding of how information evolves in these systems.
Precisely. And it's not just a theoretical curiosity either. This connection to the Bakry-Emery criterion has some very real-world implications.
Okay, I'm all ears. Tell me this has something to do with fusion energy.
You know it. One of the biggest challenges in fusion research is that these plasmas, which we're trying to use to create energy, are notoriously difficult to model and predict. But because of this decreasing Fisher information, even if you start with a rough, complex picture of a plasma, the solutions to the Landau equation naturally smooth themselves out over time, leading to more reliable simulations.
That's incredible. So this paper is basically saying, hey, even though plasmas are super complex, there are hidden mathematical patterns that make them surprisingly predictable, especially in the long run, which is exactly what we need for fusion.
You got it. And it doesn't stop there. This research also has huge implications for other fields that deal with plasmas, like astrophysics.
Okay, you've definitely piqued my curiosity. What's the connection to the cosmos?
Think about stars for a moment. They're essentially giant balls of hot, dense plasma. And understanding how those plasmas behave is crucial for figuring out how stars form, evolve, and eventually die.
So you're saying that this research, which started with a mathematical equation and some abstract ideas about information, could actually help us unlock some of the biggest mysteries of the universe.
It sounds crazy, right? But that's the beauty of science. Often the most profound insights come from unexpected places.
I love how these deep dives always remind us of those unexpected connections. Okay, before we get completely lost in the cosmos, I have to ask, are there any other practical applications of this research that we should be excited about? Let's bring it back down to Earth for a second. Besides fusion and stars, what are some tangible ways this research could impact our lives?
Well, you might be surprised to learn that plasmas are already everywhere in technology. From the chips in your smartphone to those big screen TVs, even certain water purification systems. Plasmas are essential, and this research could lead to even more efficient and groundbreaking applications.
Wow, I had no idea. It's like plasmas are the unsung heroes of the tech world.
Exactly. And the better we understand them, the more we can harness their power.
This has been such a mind-bending journey. We've gone from this equation that describes how tiny particles interact to uncovering new ways of understanding information itself. And now we're talking about implications for clean energy, the cosmos, and our everyday technology. It feels almost like science fiction.
It does, doesn't it? But that's the thing about science. It often surpasses fiction in its beauty and ability to surprise us.
Speaking of surprises, I have a feeling this research, as groundbreaking as it is, probably opens up even more questions than it answers. What are some of the mysteries that physicists are grappling with now?
One of the big ones is whether these findings about decreasing Fisher information and smoother solutions hold true for all types of particle interactions. I remember this paper focused specifically on those very soft potentials. What happens when those interactions become stronger or more localized? That's something researchers are actively investigating.
So there's a whole universe of possibilities still out there. It's like they've charted a new island on the map. But now they need to explore all its hidden caves and mountain ranges.
That's a great way to put it. Another exciting avenue is figuring out how to translate these theoretical insights into practical tools. Remember we talked about how this research could lead to more efficient simulations for things like fusion reactors? Well, turning that promise into reality is a whole other challenge, but one that mathematicians and computer scientists are excited to tackle.
So it's a bit like having the blueprint for a faster spaceship, but still needing to figure out how to build the engine.
Precisely. There's still a lot of work to be done. But that's what makes this field so dynamic and exciting.
This deep dive has been incredible. We started with this seemingly abstract concept, the Landau equation, and ended up with a whole new understanding of how information shapes the universe, from the smallest particles to the largest stars.
And let's not forget those everyday technologies that we take for granted. This research underscores just how much we rely on a deep understanding of the universe, even for things we encounter every day.
Absolutely. It's a great reminder that knowledge truly is power. And for all of you listening, here's something to ponder. If such a seemingly niche area of research can have such far-reaching implications, what other hidden connections are waiting to be discovered? What seemingly insignificant questions today might unlock the solutions to tomorrow's biggest challenges? Keep asking those questions and never stop exploring.
Ever wonder what it would take to, like, actually bottle a star?
Bottle a star.
Yeah, like all that energy. It sounds crazy, but that's kind of what physicists are trying to do with fusion energy.
Ah, I see what you mean. And you're right, it's a pretty wild ambition.
Totally. But before we even get to harnessing that kind of power, there's a fundamental thing we need to wrap our heads around: how particles in a plasma actually, like, interact with each other.
You're talking about the behavior of plasmas, which are essentially superheated gases where the atoms have been stripped of their electrons.
Yeah, exactly. And that's where today's deep dive starts, with something called the Landau Equation. Ever heard of it?
Oh, absolutely. The Landau equation is a cornerstone of plasma physics. It gives us this mathematical way to describe how those charged particles in a plasma, the ions and electrons, bump and jostle each other over time. And it's not just for things like fusion energy either. It's key to understanding how stars work, galaxies evolve, all sorts of astrophysical stuff.
So are we talking about a, like, cosmic game of billiards, but with teeny tiny particles instead of, well, billiard balls?
You're on the right track. Now, picture trying to map out how all those particles are going to move. That's where the Landau equation comes in, but it's a real bear to work with, believe me.
Why is that? What makes it so tricky?
Well, for one, it's what we call nonlinear. That means those particle interactions, they don't scale up in a nice, neat way. It gets complicated fast.
So even in theoretical physics, things can get kind of messy.
You could say that. And this is where the paper we're looking at today comes in. It tackles a big hurdle in working with the Landau equation, this thing called, wait for it, Fisher information.
Okay, Fisher information. Sounds intriguing, but I'm drawing a blank.
Think of it like this. It's how much we can figure out about a system just by looking at how it changes over time. Imagine watching a flock of birds flying, right?
Okay, got the visual.
The Fisher information in that scenario would be how much we could learn about where those birds are and how fast they're going just from seeing how the whole flock moves.
So how does the whole bird flock thing translate to, like, plasmas and this Landau equation?
Well, with a plasma, the Fisher information helps us keep tabs on how much we can learn about the particles' positions and speeds just by their interactions. Now, usually Fisher information tends to decrease over time. Makes sense, right? But the Landau equation, it's a bit of a rebel. It doesn't always play by those rules.
So it doesn't fit neatly into our usual understanding of how information in a system should behave.
Exactly. And that's why this new paper is causing such a buzz. They've managed to prove that even though the Fisher information in the Landau equation might jump around a bit, it doesn't go completely haywire. It doesn't, and I love this term, blow up.
Hold on, blow up. Okay, before we get to why this no blow-up proof is such a big deal, can you give us a peek behind the mathematical curtain? How do they actually prove it?
Okay, so imagine trying to chart, I don't know, a landscape that's constantly changing, shifting under your feet.
Okay, I think I'm following.
That's kind of what working with the Landau equation is like.
Oh, I see where you're going with this.
In this paper, they've used these really cool mathematical tools, especially from a field called information geometry. It's like they're establishing boundaries, showing how much that landscape we were talking about can actually change. They're showing that even though the Fisher information, it might jiggle around a bit, there's a limit on how unpredictable it gets.
So it's like they've given us a map, or at least some guardrails, for navigating this crazy, ever-changing terrain.
Yeah, exactly. And this whole no blow-up proof, that's huge.
Huge, Hal. Break it down for me.
Okay, so for the first time, it's telling us there's something deeper going on, a hidden order, even in these chaotic particle interactions in a plasma.
Okay, gotta ask, what does this actually mean, like, practically speaking? What are the real-world implications of being able to, make this equation behave a little better?
The possibilities, oh man, they're pretty much endless. Let's start with fusion energy. Imagine being able to harness the power of the stars right here on Earth, clean, nearly limitless energy.
That's the dream.
Right, but to make that happen, we have to figure out how to control these super hot, super dense plasmas, all held together by powerful magnetic fields.
And that's where the Landau equation comes in, right? To help us understand those plasmas.
Bingo! This breakthrough, this no blow-up thing, it could lead to much better models, more accurate simulations. We might finally be able to get a handle on how to design those fusion reactors and, who knows, maybe even make that clean energy dream a reality.
No, that would be revolutionary. What about other areas, like you were talking about astrophysics earlier?
Oh man, think about it. Imagine being able to look into the heart of a star, to build a model of how a galaxy is born, or even just start to unravel what's going on inside a black hole. This paper, this little paper, could be a key to unlocking all of that.
Okay, now my mind is officially blown. I mean, we're going from trying to understand these tiny little particles to, like, the universe itself. It's wild to think about, really. This equation, it's all about plasma, right? But somehow it might hold the answers to these huge universe-sized questions.
You're hitting on something really profound there. That's the beauty of fundamental physics. What seems abstract, even niche, can turn out to be deeply connected to, well, everything. And here's the really exciting part. This research, it's not just about understanding what we already know. It could open up whole new avenues of discovery, applications we haven't even dreamt up yet.
Okay, now I get a bite. What kind of unexplored territory are we talking about here? Give me an example.
All right, let's try thinking about it this way. This paper, it's like we've been handed a new lens, right? A new way to look at complicated systems. Yeah, we're focused on plasmas now, but those underlying principles, that no blow-up idea, it might apply to all sorts of fields where things are messy, complex, full of uncertainty.
So hold on, we're talking bigger than just physics here.
Maybe, just maybe. Think about economics, for example. What if this new understanding of how information works in complex systems could help us build better models for, say, predicting how markets are going to behave? Or even understanding why economies crash.
Now that is a thought-provoking idea. And I guess you could say the same for any field that deals with tons of data, with complicated interactions, like climate science, or even how the brain works.
Exactly. That's what makes this paper so darn compelling. It's not just about the answers it gives us, but the new questions it makes us ask. We've got these new tools now, and it's up to us to figure out what we can build.
Sounds like we're about to enter a whole new era in plasma physics, and maybe even beyond, all because someone took a deep dive into this Landau equation.
You got it. And like all the really big breakthroughs in science, this is just the first step on a long, amazing journey.
Well, listeners, I hope you've enjoyed our deep dive into the world of plasma physics and the Landau equation. It just goes to show, even in the most complex systems, there's an underlying elegance waiting to be discovered. Until next time, keep exploring, keep asking those tough questions, and as always, keep diving deep. All right, so today we are diving into the world of particle physics. It's pretty fascinating stuff, and we're going to be unpacking some groundbreaking research today on the Landau equation. Now, when you hear Landau equation, you might be thinking like, oh no, am I back in high school physics class? But don't worry,
Yeah.
This is way cooler than that.
It's not just some dry equation in a textbook.
Right, this is really about understanding how particles in a plasma interact.
Exactly.
So imagine like trying to predict the movement of a swarm of bees.
Oh,
So it's tricky,
Very.
very tricky. And for certain types of particle interactions, it seemed almost impossible to get a clear picture. But this research changes that.
Absolutely. What's really exciting here is that for the longest time, making accurate predictions about these interactions seemed impossible. The math was just way too messy. But this research really changes our understanding.
Okay, I am intrigued. So back up for a second. What exactly is the Landau equation and why should we care? I mean, it sounds pretty niche.
You're right, it might sound niche, but the Landau equation has been a cornerstone of plasma physics for decades. To put it simply, it helps us understand how energy and momentum are exchanged when charged particles in a plasma collide.
Okay.
And this is important because plasmas aren't just something out of science fiction.
Wait, really?
Yeah.
I thought those are mostly found in labs or something.
Not at all. Plasmas are actually the most common state of matter in the universe. Think about the sun, those dazzling auroras in the sky. Those are all plasmas.
Wow.
And understanding their behavior, how those particles interact, is key to unlocking some pretty significant things.
Okay.
Like making fusion energy a reality, predicting space weather that can mess with our satellites, and even understanding the very early universe.
Okay, you've sold me this equation as a much bigger deal than I thought. So tell me more about this new research. I keep seeing this term Fisher information pop up. What exactly is that?
So think of it this way. Fisher information is essentially a measure of how well we can predict where those particles are going to go. Imagine trying to predict the movement of 1,000 fireflies in a jar.
Okay.
Fisher information is like a gauge of how clear our picture is.
So the higher the Fisher information, the better we can predict where those fireflies or particles will go.
You got it. And for the longest time, we believed that this Fisher information only decreased over time. It was like our picture of the plasma got blurrier the longer we looked at it.
Okay. That makes intuitive sense, I guess.
Yeah.
But this research is saying that's not always the case.
Exactly. This research has found that for certain types of particle interactions, the Fisher information doesn't just decrease, it actually gets better over time.
Hold on. So her picture of those fireflies in a jar, it actually becomes clearer the longer we watch.
Yeah.
How is that even possible?
That's the million-dollar question. And that's what makes this research so groundbreaking. To understand why this is such a big deal, we need to delve a bit deeper into the type of interaction they focused on, the Coulomb potential.
Okay, now you're just using big words to make me feel like I skipped physics class. What is this Coulomb potential thing?
It's simpler than it sounds. At the heart of it is something called the Coulomb potential, essentially the force that charged particles exert on each other. It's what makes lightning crackle and your hair stand on end with static. Now, this force gets really strong at very short distances, which used to make predicting long-term behavior in plasmas incredibly difficult.
So it's like trying to predict where a bunch of magnets are going to fly in a box. Things could get pretty chaotic. And this research is saying we can actually predict that chaos.
Precisely. And not only predict it, but we can actually see a clear picture of it over time. This finding completely changes how we think about these types of interactions.
This is blowing my mind. So are you saying we can actually simulate those interactions with more accuracy now?
Exactly. And that brings us to another amazing discovery in this research, the existence of smooth solutions.
All right, break it down for me, smooth solutions. What in the world does that even mean?
It means that the mathematical description of how the plasma behaves doesn't have any sudden unpredictable jumps or breaks. Think of it like drawing a line on a graph with smooth solutions. We can draw that line continuously without having to lift our pen.
Okay, so instead of a line full of zigzags and sharp turns, we're talking about a nice, smooth curve. I have to admit that does sound a lot more predictable.
Exactly. And this smoothness is particularly significant given the strong localized forces at play with the Coulomb potential. Previously, when models tried to predict what happens when these particles get too close, things would get messy. It was like the Coulomb force caused these sudden, unpredictable jumps in their behavior.
It's like those magnets we were talking about suddenly snapping together.
Yeah.
That's kind of unpredictable.
Yes. But what this research shows is that even with these strong interactions, we can still have a smooth, continuous description of how the plasma behaves over time. It's a remarkable finding that opens up a lot of possibilities.
So we've got these two groundbreaking discoveries, increasing Fisher information and smooth solutions. It's like we've suddenly got this crystal clear, slow motion replay of those magnets flying around.
Yeah.
But what does this actually mean for, well, the average person? It all sounds pretty complex.
It is complex, but it has some really exciting implications for a wide range of fields. Let's start with fusion energy.
Okay, because fusion energy always feels like the holy grail of clean energy, the dream that's always just out of reach.
You're right, it's been incredibly challenging. But this research could be a major step towards making that dream a reality. Imagine a future where we could power our homes and cities with a clean, nearly limitless source of energy.
Okay, I'm definitely picturing it. And you're saying this research gets us closer to that. How so?
This discovery allows us to create more accurate and reliable simulations of how plasmas behave, especially over long periods. And that's crucial for something like fusion energy, where we're trying to contain and control extremely hot, dense plasmas.
So it's not just about understanding the science anymore. It's about applying it in a really tangible way.
Exactly. And it goes beyond just fusion energy. Think about things like designing more efficient electronics, developing new medical technologies, even understanding the weather patterns on other planets. This research has the potential to impact so many aspects of our lives.
I'm starting to feel like this one research paper is a portal to a whole new world of possibilities. It's pretty incredible when you think about it. Something so seemingly abstract can have such tangible, real-world implications.
Yeah.
But I have to ask, is this really the whole story? What are the next big questions? What are the mysteries that still remain unsolved?
That's the beauty of scientific discovery. Every answer leads to more questions. We've taken a giant leap forward, but there's still so much we don't know. For example, this research focused on a specific type of particle interaction. But what about all the other ways particles can interact in a plasma?
So it's like we've mapped out one small corner of a vast uncharted territory.
Precisely. And now we have the tools and the knowledge to start exploring the rest of it. Imagine what we might discover as we delve deeper into this world. The mysteries of dark matter, the behavior of black holes, the very origins of our universe.
It's incredible to think that we've only just begun to scratch the surface of understanding plasmas.
It really is, and what's so fascinating is that this research gives us a new set of tools to explore even more complex scenarios.
Okay.
Places where plasmas behave in ways we can barely imagine.
Okay, now you're just teasing me. What kind of scenarios are we talking about?
Think about extreme environments like those found in neutron stars or black holes. These are places where matter is squeezed to unimaginable densities, creating plasmas unlike anything we see in a lab.
Okay, now that's next level stuff. Neutron stars and black holes we're talking about, unlocking the secrets of the universe here.
Exactly, and it's not just about understanding those cosmic giants. This research could also give us insights into the formation of galaxies, the behavior of matter under extreme pressure, and maybe even provide clues about the fundamental laws of physics themselves.
Wow, so this one paper about particle interactions might hold the key to unlocking some of the universe's biggest mysteries. It's mind-boggling.
And that's the beauty of science, the interconnectedness of it all. We started with this seemingly abstract equation, and now we're talking about black holes and the origins of the universe. It's a reminder that every discovery, no matter how small, has the potential to open up entirely new avenues of exploration.
I am officially in awe of the power of curiosity. This has been an incredible journey. So where do we go from here? What are the next steps for researchers in this field?
Well, now that we have this greater understanding of how certain particles interact in a plasma, we can start applying this knowledge to more complex systems. Imagine running simulations of the plasma around a black hole or recreating the conditions of the early universe in a lab. These are the kinds of questions that researchers will be tackling in the years to come.
It feels like this research has opened a door to a whole new world of possibilities, a whole new era of understanding in plasma physics.
And to think it all started with someone asking a simple question: what if we could predict how these particles behave with more accuracy? It's a testament to the power of curiosity and the incredible things we can achieve when we dare to explore the unknown.
You've given us a lot to ponder today and a whole lot to be excited about. Thank you for guiding us through this incredible deep dive.
It's been my pleasure. Until next time. All right, let's dive into this. We're tackling some pretty intense research. I took a look at what you sent over about Sehyun Ji's paper, Dissipation Estimates of the Fisher Information for the Landau Equation. Wow, this is some next level stuff.
It really is cutting edge. We're trying to wrap our heads around how systems of particles, how they change over time, all driven by how they bump into each other.
Okay, so for those of us who haven't exactly been hanging out with plasma physicists lately, can we break this down? What even is the Landau equation? What's it do for us?
Okay, so picture this. Imagine like a cosmic pool table, right? But instead of those nice solid billiard balls, you get these tiny charged particles.
Yeah.
And they're constantly bouncing around, bumping into each other, influencing each other. So the Landau equation, it basically gives us a way to model all those collisions. It's all driven by things like electrostatic forces and stuff. It helps us see how the whole system, how it behaves overall.
So we're not just talking about a frozen moment, right? We're talking about understanding how all these particles do their thing, how they interact. The whole dance.
Exactly. And the dance gets even wilder when you throw in the whole concept of Fisher information.
Okay, hold on. Fisher information sounds kind of deep. What's that tell us about our cosmic pool table?
So think of it like this. Fisher information, it's kind of like a measure of how much order we can actually see in the whole system. Like high Fisher information, that means we can pretty much pinpoint where each particle is, how fast it's going. We can follow along with their moves. Low Fisher information, that's where things get messy, more chaotic, less predictable.
Gotcha. So high information is we've got a detailed map of the dance floor. We know every particle's steps. And low information, that's what? A mosh pit. You just see a blur. Organized chaos. Right?
You got it. And here's where things get really interesting. Mathematicians, they've been trying to figure out how the Landau equation, how it affects this information over time. Does the dance always get more chaotic? Do we always lose that initial order?
Sounds kind of like we're talking about entropy, right? The whole idea that everything kind of tends towards disorder.
You're picking it up fast.
Yeah.
And this is where those mathematicians, Gillen and Silvestre, they made a breakthrough. They figured out that, yeah, under the right conditions, Fisher information, it does go down as the particles interact. It's like, if you're watching those particles in our cosmic mosh pit, they just get more and more mixed up. And eventually, you can't tell who's who anymore. You lose track.
Whoa. So you can't rewind, no going back to that initial order.
Exactly. And that's where Sehyun Ji, he comes in with his research. He adds another layer.
Okay, so we know the dance gets crazy eventually. What did you find out?
He found a way to measure how fast that info disappears, how fast that initial order, dissipates. It's like, imagine you're trying to guess how fast two gases would mix together. Ji's research gives us that kind of predicting power, but for all that complicated stuff going on with the Landau equation.
So it's like he found a speedometer for chaos. How do you even do that? I saw the paper mention something called dissipation estimates, which honestly sounds crazy complicated.
It is complicated, but I think we can break it down. He used this really powerful math tool. It's called a cutoff technique. Basically what it does is it lets him take the Landau equation and sort of, dissect it, focus on the specific parts that really control how fast the information goes away.
So he's like a surgeon zeroing in.
Yes, smart. Yeah. And what he found, super insightful, he found this specific mathematical relationship, an inequality, in the math world. And it links how fast the information gets lost to the forces that are making those particles interact in the first place.
Hold up. So stronger forces mean faster disappearing information.
Exactly. And his work gives us the framework to measure it, which is a huge EE step.
This is where it gets really cool. We started with this kind of abstract particle party, and now we can actually put numbers on how fast things get unpredictable. But so what? Why does all this matter?
That's the amazing thing about this kind of research. It might seem abstract, but it's got real-world implications.
So this isn't just theoretical, right? Knowing how fast information disappears with this Landau equation stuff, there's got to be real-world stuff, yeah.
Oh, yeah, definitely. Big one. Fusion. Like, if we want to make fusion power happen, really make it work, we've got to nail how plasmas act. It's all about prediction.
And plasmas, those are like the poster child for the Landau equation, right?
Yeah.
Tons of charged particles all bouncing around.
Got it. And because Jin figured out this way to measure how fast the information gets lost in these systems, that could make our simulations way more accurate.
So we're not just saying, okay, the plasma is going to get chaotic eventually. We can actually say how fast. How does that help us build a better fusion reactor?
Think of it this way. The more we understand how a plasma is going to act, the better we can trap it, control it, right? Which is like the whole game with fusion. Ji's research, it helps us fine-tune how we think about that whole information loss. Could be the key to making fusion power a reality.
Okay, I'm starting to see it. Clean energy, game changer. And Ji's research might be a part of that, but fusion's not the only place where this stuff matters, right? Understanding these crazy interactions, it's got to be useful somewhere else.
Oh, tons of places. And that's the cool part. This fundamental research, it pops up everywhere. You'd never expect it. Think about self-driving cars.
Self-driving car. Okay, now that one I didn't see coming. How does this connect?
Okay, so if you want to predict how cars are going to move in traffic, make sure they don't crash, make them efficient, you need some serious algorithms, right? Algorithms that can process tons of data, tons of interactions. The more we know about information loss, information gain in these systems, the smarter those algorithms can be.
So it's like we're making the cars more aware. They can understand what's going on around them and react better.
Exactly that. If we can figure out how uncertainty spreads through the system, it doesn't matter if it's plasma or a highway full of cars, we can build more reliable systems that don't break down.
That's wild. We went from the inside of a fusion reactor to self-driving cars. And it all goes back to this whole idea of information, disappearing, dissipating.
It shows you how connected everything is. What you think is some obscure math concept, bam! It's got real-world uses. You wouldn't believe it.
That's what I love about these deep dives, right? We're not just skimming the surface. We're going deep, finding the connections.
Couldn't have said it better myself. And honestly,
yeah,
this is just the beginning.
Wait, seriously? There's more. What else can Ji's work do? More. Seriously.
Yeah.
What else could come from this?
Well, we've talked about fusion, right?
Yeah.
Self-driving cars. But it goes even further than that. Remember that cutoff technique, the one Ji used to, break down the Landau equation?
Yeah, he honed in on how the information gets lost, right?
Exactly. And that's what's got everyone excited. What if we could use this technique, this new way of thinking, on other equations, other models that, describe how things work. We would be talking about like totally new discoveries, how galaxies behave, even like the fabric of space-time itself. Crazy stuff.
Yeah, okay. Now that's a deep dive. We started with this like abstract math stuff, and now we're talking about like the biggest mysteries in the universe.
I know, right?
Talking
Like,
about
gee, he wasn't even trying to like rewrite physics textbooks or build a better car. He just wanted to understand this one fundamental question about information and chaos. And boom, he opens up all these new doors. We didn't even know they were there.
you really start to see how it's all connected, all this knowledge. And we found it all from just digging into this one paper.
That's what we do here, right? We find the connections, those aha moments. It's like you suddenly see the world differently.
100%. So for our listener today, they're obviously into this stuff. What would you say is like the big takeaway from G's work?
Hmm. That's a good question. I think the biggest thing to remember here is even if the math seems, I don't know, out there, it can have huge consequences. G's a perfect example. Never underestimate the power of a good question,
Yeah.
Even the really basic ones. It can change how we see the entire universe.
Well said. It's like that saying, right? The more you learn, the more you realize how much you don't know. G's research, it's just like throwing out all these new questions. That's what makes this whole field so amazing.
For sure. What a time to be like exploring the edges of what we know.
Absolutely. So to our listener, keep those questions coming. And until next time, keep diving deep. All right, everyone, buckle up. Today, we're taking a deep dive into the world of plasma physics. And let me tell you, the research you sent over sounds pretty intense.
Yeah, it's it's definitely a brain teaser, but that's what we're here for, right?
Exactly. We're tackling this paper on the Landau equation. And I gotta admit, that title, Dissipation Estimates of the Fisher Information for the Landau Equation, it's a mouthful.
Yeah, it's not exactly light reading, but trust me, the core ideas here are incredibly cool and have some really big implications.
That's what I'm counting on. So for our listeners who might not be familiar with it, what exactly is the Landau equation? What's the big deal?
Well, in a nutshell, the Landau equation describes how charged particles in a plasma, things like electrons and ions, interact with each other over time.
Okay, so like a plasma is like the stuff they use in those fancy TVs.
Well, sort of. Plasma is actually considered the fourth state of matter. It's like a gas, but the atoms are superheated to the point where they lose some of their electrons, leaving behind a mix of charged particles. And this creates a really interesting and complex system with all sorts of cool properties.
Ah, okay, so it's not just about fancy TVs then.
No, not at all. Plasmas are everywhere. The sun is a giant ball of plasma. Lightning bolts are plasma. Even those neon signs you see are filled with plasma.
Wow. Okay, so it's everywhere and it's complicated. And this Landau equation, it helps us make sense of all that chaos.
Exactly. It's a mathematical tool that helps us predict how those charged particles in the plasma will behave over time. But it's tough because plasmas are incredibly dynamic. The particles are constantly colliding and influencing each other through these electromagnetic forces.
Oh, I bet. So predicting the behavior of plasma, it sounds like trying to predict the weather, but on a whole other level of complexity.
That's a really good analogy. It's like trying to predict the movement of a million tiny billiard balls all bouncing around and colliding with each other at super speed.
Yikes. Okay, yeah, that sounds intense. And to make things even more complicated, I've heard something about Fisher information being important here.
You're right, that's a key concept in this research. Imagine you're trying to take a picture of a hummingbird in flight.
Okay, beautiful but quick.
Exactly. You need a really fast shutter speed to capture a sharp image, right? Fisher information is kind of like that shutter speed, but for our understanding of a system.
So higher Fisher information means a clearer, more precise picture of what those plasma particles are doing.
Exactly. It tells us how much information we actually have about the system and how confident we can be in our predictions.
Gotcha. So where does this paper fit into all of this? What's the big breakthrough?
Well, this paper, it actually proves something really remarkable. It shows that for certain types of Landau equations, the Fisher information never decreases over time.
Hold on. So even though those plasma particles are constantly bumping around and interacting, our picture never gets blurry? That sounds kind of impossible.
It's definitely counterintuitive, but that's the beauty of this finding. It's like having a magical camera that takes a super sharp picture of the plasma, no matter how much those particles are moving and shaking.
Okay, wow, that's huge. But why? Why does that matter so much?
Well, for one thing, it gives us a lot more confidence in our ability to make accurate predictions about plasma behavior, even over long periods. And this has some really exciting implications for things like fusion energy research.
Right. Fusion energy, that's like the holy grail of clean energy, isn't it?
Exactly. And to achieve fusion, we need to be able to control extremely hot, dense plasmas. This research could help us do just that by giving us more accurate tools to predict how those plasmas will behave.
That's amazing. So we're talking about potentially revolutionizing energy production, all thanks to a deeper understanding of some pretty abstract math.
That's the power of fundamental research. But it gets even better. This paper doesn't just stop at proving the Fisher information never decreases. It also tackles a particularly tricky aspect of the Landau equation called very soft potentials.
Very soft potentials. Okay, you're losing me a bit. What are those?
So imagine those charged particles in the plasma are like tiny magnets.
Okay, got it.
In most plasmas, those magnets would only interact strongly with other magnets that are very close by, right?
Right, makes sense.
But with very soft potentials, it's like those magnets suddenly become super strong and can interact with other magnets from much farther away.
Ah, so even a tiny nudge on one side of the plasma could have a ripple effect across the entire thing.
Exactly. It creates a much more complex web of interactions that are really difficult to model mathematically.
Wow, okay, yeah, that sounds like a nightmare to try and predict.
It is, but that's why this research is so groundbreaking. It proves that even in these extreme scenarios with very soft potentials, that never decreasing Fisher information still holds true.
So it's like we found a way to make sense of the chaos even when the rules of the game get a lot more complicated.
Exactly. And not only that, but this paper also delves into the idea of smoothness in solutions to the Landau equation.
Smoothness. Okay, now I'm really curious. What does that mean in this context? Smoothness, like a baby's bottom smooth. I'm not sure I see the connection to plasma.
Well, not exactly, but it's a good way to think about it.
Yeah.
In this context, smoothness means that the solution to the Landau equation, the way we predict the plasma will behave, it doesn't have any sudden crazy jumps or discontinuities.
Oh, I see. So it's more like a smoothly flowing river instead of a wild waterfall with like unpredictable splashes and stuff.
Precisely. Smoothness means things are changing in a more predictable, continuous way. And that's really important for making reliable predictions about how the plasma will behave over longer periods.
Makes sense. So this paper, it shows that these smoother, more predictable solutions, they actually exist even when we're dealing with those tricky, very soft potentials.
Exactly. It's like we've found a way to tame the chaos, even these really complex scenarios. And that's a big deal because it gives us a lot more confidence in our ability to model and predict plasma behavior in a wide range of situations.
This is all starting to come together now. So we've got this super important equation that describes how plasmas work, but it gets really complicated when we factor in those long-range interactions. And this research is basically telling us, hey, even when things get wild, there's still an underlying order and predictability to it all. We can find it.
Exactly. And the implications of that are huge. I mean, think about it. This kind of research could revolutionize fields like fusion energy, astrophysics, you name it.
Absolutely. We're talking about unlocking cleaner energy sources, understanding the cosmos better. It's mind-blowing.
It really is. And the best part is this is just the beginning. This paper focused on a specific type of Landau equation, but there's a whole universe of plasma behaviors out there waiting to be explored.
It's like we've just scratched the surface of what's possible.
Exactly. Who knows what other secrets these equations hold and how those discoveries might change our world?
Well, I, for one, am excited to find out. Thanks for taking us on this electrifying deep dive. I feel like my brain just got a serious workout.
Mine too. It's always a pleasure to explore these fascinating topics. Until next time.